Hello and welcome to the Intro to EMG. Today we are going to discuss what an EMG or electromyography signal is, how to handle it, and how to apply it to real-world scenarios. My name is Zach Scarano and I will be bringing you through this topic today. Let's begin. Electromyography deals with the detection, analysis, and utilization of electrical signals emanating from skeletal muscles. The electric signal produced during muscle activation, known as the myoelectric signal, is produced from small electrical currents generated by the exchange of ions across the muscle membranes and detected with the help of electrodes. This signal is represented in units of microvolts. Now, the human body is a wonder of nature. We all know this. In particular, motion of the human body is a perfect integration of the brain, nervous system, and muscles. Altogether, it is a well-organized effort of the brain and 28 major muscles to control the trunk and limb joints to produce the forces needed to counter gravity, propel the body forward, as well as countless other functions through which we can interact with the world around us. EMG allows us to see inside the body and understand how well the brain and musculoskeletal system are coordinated. Muscles are innervated in groups called motor units. A motor unit is the junction point where the motor neuron and the muscle fibers meet. When the motor unit is activated, it produces a motor unit action potential. The activation from the central nervous system is repeated continuously for as long as the muscle is required to generate force. This continued activation produces motor unit action potential trains. The trains from concurrently active motor units superimpose to produce the resultant EMG signal. In short, EMG is the process of measuring the summation of these action potentials, which results in a bipolar signal representing the neurological recruitment of a muscle. When performing an EMG analysis, it's important to evaluate the raw signal before collecting any data. This will assist you in confirming the quality of your recording, as well as showcase any interference that may be present in your recording environment. The raw signal should be free of baseline noise. To check this, a subject must assume a position in which they can completely relax the muscle of interest. A muscle that is not turned on should not have any muscle activity, and therefore, your EMG reading should be nearly zero. Average baseline noise should not be higher than 3 to 5 microvolts, although 1 to 2 is the target. But this really depends on the EMG amplifier quality, as well as environmental noise and proper skin and site preparation. Meticulous site preparation can dramatically reduce the impedance level and improve the output voltage as well as the resilience of the signal against environmental artifacts. Ideal impedance is less than 20 kiloohm, but if you can get this value below 10 kiloohm, environmental artifacts will essentially be eliminated. Skin preparation can be approached in a few different ways. Typically, an alcohol swab is used to just clean the surface of the skin. However, it's recommended to also use an abrasive cloth or gel to remove any dead skin cells from the surface of the skin. These dead skin cells are precisely what are causing the high impedance levels. As mentioned previously, With good skin preparation, better signal qualities can be achieved. Now that you have a noise-free baseline, you can begin recording the signal. And once you have data recorded, there are signal processing procedures that are undertaken so that you can begin to interpret your recording. The raw EMG contains basic information and documentation of the muscle innervation. On, off, more or less, and timing characteristics, which are all qualitative assessments, can be roughly assessed with the raw EMG signal. But if quantitative amplitude analysis is of interest, then specific signal processing steps should be applied. These basic signal processing procedures, such as rectification, smoothing, and other filtering options, allow you to answer the most basic EMG questions, which we will discuss here shortly. Rectification is the process of taking the absolute value of the signal. Since the EMG signal is a bipolar signal with symmetric distribution of positive and negative amplitudes, standard amplitude parameters, such as taking the mean, would result in a zero value. Rectification allows us to calculate these standard amplitude parameters by looking at the absolute value of the signal. A smoothing algorithm can be applied to outline the mean signal trend of the signal, essentially creating an envelope of the rectified signal. This approach allows for easy visualization of the rise and fall of an EMG signal, as well as the peak intensities achieved. Additional filtering can also be applied to remove noise artifacts if necessary. The EMG signal lies in the frequency range from 0 to 500 Hz, but is most dominant between 50 and 150 Hz. That said, it's possible to apply a high and low pass filter to delete noise frequencies that may be contaminating the raw EMG signal. Typically, these noise frequencies are occurring below that 50 Hz or above that 150 Hz level, and may be caused by such things as motion artifact or even infiltration of other electromagnetic signals from different wireless devices. Now that we've addressed the raw signal and looked at the different processing techniques, we can now answer the most basic EMG quantitative questions. For starters, EMG can tell us something very simple. Is the muscle on or is the muscle off? For example, we can see in this image here that this muscle, the vastus lateralis, has peak activation when our subject is reaching toe off during running. The coordination of that muscle with what's occurring kinematically can allow us to see how well that muscle is being recruited and if it's being recruited at the right times. Additionally, we can also see when the muscle is activated. So not necessarily is it just on or off, but precisely when does the muscle activate? In this example, we're looking at, does the deltoid activate at the proper time after being cued from a visual stimulus? Using this approach, we can look at things such as reaction timing or understand the proper coordination pattern from one muscle to the next if we want to see certain principles of movement related to firing patterns, let's say from proximal to distal activation. Next, EMG allows us to understand the intensities of those muscle firing. Is the muscle more or less active? For instance, we can see in the anterior lat pull down, the posterior deltoid is not very active. However, in the posterior lat pull down, now that posterior lat deltoid is engaged in part of the stabilization and force generation necessary to move the weight. Using EMG to compare different activities and seeing how the coordination patterns and the muscle activity intensities change is one of the most common use cases for EMG. Other EMG analysis techniques include looking at the frequency components of the signal. Typically, the frequency components are used to identify when a muscle is fatigued. We can look at changes in the mean and median frequency, as well as how many times the bipolar signal crosses 0. And then also understand the mean amplitude of the signal as it changes over time. Does it rise or does it fall? Each of these parameters and assessing how they change over time gives us the ability to understand that muscle recruitment pattern and how it changes as things progress, as things become more difficult, or as this muscle becomes more tired. For example, when performing an isometric contraction, we can see at which point the muscle begins to fatigue, as well as the compensation patterns that might occur from repositioning the body. Frequency domain and spectral domain features are used to assess that muscle fatigue and motor unit recruitment. So decreases in motor unit recruitment occur as the conduction velocity slows when the muscle gets tired, and can therefore be evaluated by looking at those frequency changes of the EMG signal over time. In this example, we can see which muscles have fatigue during the contraction period by seeing this decrease in frequency over time. We can also evaluate the rate of fatigue by looking at the slope. Other than physiological and biomechanical research, EMG has been developed as an evaluation tool in applied research, physical therapy, rehabilitation, sports medicine and training, as well as ergonomics research. For instance, in rehabilitation, EMG can be used as a biofeedback tool to help a patient understand their muscle recruitment and effectively make adaptive changes by interacting with the EMG signal during exercises. Using biofeedback, patients can reconnect motor pathways to a muscle and eventually relearn how to incorporate those muscles in their daily activities. If we look to this example, we can see this gentleman interacting with the EMG signal on the computer screen as he's going through these leg extensions. With consistent practice in understanding what positions he needs to be in to recruit that certain muscle, simply just engaging it and recreating that motor pathway, he'll then be able to engage that muscle during his activities of daily living, thus creating a more stable base for him and improving his overall health condition. It's these applications that make EMG such an incredible technology to use for so many different applications. So I want to thank you for joining me today for this short discussion on the exciting and insightful practice known as electromyography. I hope this piqued your interest and that you continue to explore this concept and technology. Please feel free to visit our website to learn more. Thank you.